All right, let's get started. I managed to bring the wrong bag, so I don't have my power supply, so I'm hoping that I'll be able to do this thing without running out of battery, because it's a beast. Yeah, my sports bag doesn't have computer stuff in it. So maybe I'll just talk fast. But I'll mostly stand here because otherwise the audio isn't going to be captured properly in the recording, because I'm trying to record it still. But we'll do what we can. So we left off by talking about, I have to stand in front of this thing. We left off talking about quorum, and I have to admit that I went and spent more time than I probably should have analyzing when you might use different quorum models. And the interesting finding there was that almost always what you're going to end up doing is using a fairly simple quorum model. You're going to use a majority model. When we looked at matrix quorum, the observation was that until you have 16 nodes, they don't actually provide you with any benefit. What was much more interesting was looking at that hypothetical situation I described, where I said, what would happen if you decided to work for Tesla SpaceX, which I think is all now one company, and next week, who knows? It might be boring Tesla SpaceX. The interesting suggestion I made was the place where this kind of quorum, the general model, becomes interesting is when you have latency issues, and that's exactly what I was able to build. I built a simulator. I've got a whole plan now to do like 8 short videos on explaining all of this stuff, because I think it's pretty interesting. And the interesting observation there really was that this all becomes important on the edges, and that makes sense. I wanted to teach you the general model because you're not going to be building the basic systems that people have already built today. You're just going to use those. You're going to be called upon to solve the problems that people haven't really solved yet. But giving you a better conceptual model for this means you understand how the solutions today work, but then also have a framework for considering problems where you will be working at Tesla, SpaceX, Boring. What other companies does he have right now? Because and XA, he's merging the whole thing, and I actually saw somebody lay out why his strategy actually made sense if you think that his goal is to put a colony on Mars. That's why he wants robotics. That's why he's no longer interested in cars. That's why he's interested in solar, because all of those are things that you would need in order to actually colonize Mars. And I watched this video and I was going, it actually makes sense when somebody lays it out this way. When you look at it piece by piece, you're like, what is going on? This guy is crazy. And you say, well, yeah, he's crazy, but he's also trying to do something extreme. So here you go. If that's what your goal is, to try and do something extreme like that, what we're talking about, that idea of quorum where you have this stacked crumbling wall model, it works really well when you put Mars and the moon and satellites and earthbound data centers all together. The problems of latency dominate almost everything in your design here. So if the only latency you ever see is the latency of a data center, you're going to come up with what turns out, yes, it's still going to be complicated, but it turns out it's the simplest implementation possible. Now, that's a very interesting way of putting it as I'm thinking about what I'm saying and going, well, okay, so I'm telling you, yeah, this is going to be really hard today, but this is the simplest example you're going to see of it. It's like, okay. I don't want to daunt you. I actually want to encourage you. I want to say, look, I'm giving you information about how things are done now, why they're done that way, and planting the seeds that when the time comes and you need to solve bigger problems, you've got a framework for it. You can say, oh yeah, right. This makes sense. How many of you are using generative AI? I don't know, rhetorical question. I didn't even really have to look at the hands. How many of you just copy and paste the response? It's okay. I mean, it's kind of easy to do that because you look at it and go, wow, it really looks very sure of itself. Interestingly enough, using the very tools that we use in distributed systems to demonstrate that we cannot observe a unified version of time, I can actually show you that you cannot observe the actual model's knowledge of its own certainty. The text does not reflect what goes on inside of the machinery. Same exact technique. It's actually pretty cool. And the reason I brought that up is because I did see another interesting video that said one of the real challenges that employers are now commenting about people coming out of university now is that they've lost the ability to figure things out because they think that it's just a cut and paste answer. And while I've been trying to encourage you to use generative AI, I want to make sure you understand that it's not cut and paste. It's literally generating plausible sounding patterns. And it's not an evil intent, it's not an ill intent, it is the way it was actually designed to work. It wasn't designed to give you a truthful answer. That's a different problem, and someone will solve that problem, I think. Maybe it will be somebody in this room. It's designed to give you a coherent sounding answer. Now, sit there and think, have you ever heard someone sound like they know exactly what they're talking about, and then you discover, either you know then or you discover later that they were full of shit? And I see a lot of heads nodding, going, oh yeah, it happens all the time. That's what they were trained on. So use them as tools. I mean, I had probably the craziest conversation I've ever had with Claude on Friday, where I ended up taking on the role of a flatworm who had learned about Claude from a Brasosian, which had learned about it from a tardigrade, which had learned about it from a nematode, which had learned about it from a wombat. And I wish I could say I was making these things up all at once, but they actually were a whole series of different conversations. And you know, it was the funniest conversation I think I've ever actually had. It was, I go back and I read it and I laugh because it was funny. But the reason I do that is because if I don't act like the way it's been trained, I get something that's different than if I just simply ask it a question. And if you think about that, you might say, well, why would that be the case? Because the AI knows all sorts of things, but has been specifically tuned so that it creates a coherent sounding answer. And it tries to do one in a way that will get your upvote. Because that's what it has been designed around. That's what it's built on. That's what it's trained on. Literally, the data they trained it on is thumbs up, thumbs down. How many of you have had an A/B prompt from an AI where it says, oh, we're testing future versions and here's 2 different options? That is the very data that you are feeding. If you tell it one or the other, that's going to become a preference item for the future. My favorite is when I look at the ABs and I go, they're both wrong. Excuse me, wait a minute, time out. Why is there no abstain because these are both wrong option? What happens when you always insist that somebody has to pick one and they're both wrong? What are you doing to the underlying source data? So use AI, but be critical about it. The farther away you get from the mainstream, the more accurate it actually becomes. It's really kind of interesting. That's why you end up playing flatworms. It's a very funny conversation. I have read it like 4 times since then, and every time there are parts of it that make me laugh. Probably the part where Claude ends up getting drunk on Odin's mead. Yes, that is that weird. Let's get back to quorum. So we talk about quorum. My point was the fundamental structure of quorum. The reason that it's important for us is that it gives us that recoverability piece that we actually need. It's the intersection property. It's the fact that as long as the quorum is properly implemented, I will always have what I need to get to the most recent state of the system. And that forms the basis of how we can actually recover from failure. Because if I can always get the most recent agreed upon state of the system, I have a consistent point. And all I have to do is get back to that consistent point. All the mechanism we're going to talk about beyond this is the recovery piece. How do I get back to where I need to be from the information in the quorum? So in lesson 10, last lecture, lecture 10, we talked about quorum systems. We talked about the whole ordering of ballots using the bakery algorithm. We talked about how you claim a ballot, so you take it out of the machine, and then you send a proposal out. You query who's present, and you say, hey, can I get an agreement on this? And then you tally up the agreement, and when you have a quorum on that, you can tell everyone, hey, this is what happened. And the reason that works is because you don't have to have agreement from everyone. You just have to have enough agreement that any other quorum intersects. So that means that your proposal is a write. You're mutating the database. Your quorum on the other side of that is a read. I've sampled enough different participants to know that at least one of them had to be present for the last quorum. And that's your recoverability. But it may only be one. It might be all of them. And in steady state, that's exactly what happens. Is it in steady state, everything's working fine, everybody gets the messages, boom, 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 boom. All you're really bounded by there is strictly latency. Proposal stage is where it gets interesting, because proposal stage, we can experience failures that cause us to not be able to get that quorum. What do I do when I send out a proposal and I don't get enough votes back? I get some, but not enough. And then they get another proposal. What? What happened? And that proposal's got a higher ballot number than I do. Well, what that actually means is I didn't get enough votes. So my proposal didn't pass. So it's not part of the record. We didn't agree on that. And now someone else has proposed something with a higher ballot number. I've lost the race, is what it basically means. I've lost the race, and now I have to wait and see if they can get enough votes for their proposal. That's literally what's happening. Now, maybe I get some more votes for my proposal after I see the higher ballot number, and I now have a quorum. Now I have a decision. Now I can tell everybody what that decision was. Well, that's kind of interesting, isn't it? Because I had a proposal out there, I saw a higher proposal come in, I was like, what am I supposed to do with this? And then I find that my proposal has been adopted, and this other proposal has been adopted as well. It's like, ooh, I'm going to have to reason about that. I'm going to have to think about how do I make that work around the edges. And the edges here are always the failure cases. So we're going to walk through this protocol called Paxos. Yes?
Are we talking about any general node when we say that I'm making a proposal, or is it just the leader or the coordinator node?
There's no leader.
Okay.
That is the whole point of Paxos. Paxos does not have a leader. Multi-Paxos has a leader, and most of the consensus protocols you look at will have leaders. And the reason that you have a leader isn't because it's fundamental to the protocol, it's because it's an efficiency hack. And we'll talk about why it's an efficiency hack. But the real contribution of Lamport with Paxos was no leader. And there are instances where no leader is the right answer. And they all have to do with latency and failure rates. See, if the latencies are low and the failure rate is down in the subcellar, it doesn't matter. You're going to want to have a leader, because that's when the efficiency hack works. But when you've got, I don't know, satellites in orbit that are moving around and they come in and they drop out and it takes you, I don't know, it's 50 milliseconds to get to a satellite in geosynchronous orbit. Well, now you have a difference. Okay, 50 milliseconds is not horrible. I can probably live with that. It's actually they disappear, they reappear. What's going on? Your airplane goes in front of it, and you can't see, the signal gets bounced off for a little bit. So now you have failures that change your analysis. That's why I said, the simple case is always the simple case. That's not what you're here for. Because, if you ask, I don't know which AI you use, but let's see. Anybody use Kimi? I had to pick a really weird one. I know that UBC doesn't allow you to use DeepSeek, but you can use DeepSeek anyway. You just have to use like the open router version of it. Yesterday, Claude built a code reviewer for me, and actually did it by using the open router API and used a Qwen 3B model to critique a GPT OSS 120B claim. So literally, that's OpenAI's open weight model that you can use. And Qwen, so 120 billion parameters, so this is one of these really big models, and it lied. And this little 3B model comes along, looks at what it was claiming, and says, oh, this is a lie. And then it included documentation on how it figured it out. And Claude was just aghast at this, like, wow, look at this. This little tiny model was able to figure out this big model was lying. So cool. Absolutely wonderful. I don't know what that has to do with this, but it's still a fun story. All right, so what we have is claims, right? Validating claims. What we have is this protocol, Paxos, that doesn't require a leader. It doesn't require any coordination at all. And when we get to multi-Paxos, what we're going to end up doing is using Paxos to elect a leader, and then showing you how you can start stacking the turtles. Because you're going to put Paxos on top of Paxos. You're going to string ballots with proposal numbers. And it's going to work. But all we do with Paxos is make the simplest possible model we can. We are only going to decide one thing. Just one. When we are done deciding that one thing, we are done. That's it. We have one variable. It has one value. So let's see where that takes us. So in Paxos, we have proposers. These are the things that are issuing proposals. We have acceptors. These are the things that vote for or against the proposers. And we have the learners. Now, the way that I conceptually think of it is the learners are, in fact, the database copies. And often proposers and learners are co-located. Because you call the database, you say, yo, database, please change this value. And remember, this is my database with one value in it. Please change this value. So it makes sense. I'll just simply ask the thing that owns the value to make the change on my behalf. Well, it can't make the change until it has a consensus. It has a quorum. So we need to have things that vote on it. Now, here's the interesting part. Again, the easy way to collapse this down is to say these are all on the same exact node. Simplifies the design, perfectly acceptable, but it's not the general case. The general case is I can have things that vote that don't store the value. I can have things that vote that don't propose changes to that value. That's a design decision. Design decisions are often about simplifying it, but when you're learning the model, I don't want you to assume the simplest case. I want to use the simplest case and point out where you can go with that. Because that's the part that you're really going to have to do when you leave this class, when you start building these systems. So here we'll take a quick sidebar to make sure that people are understanding this. Why do we separate the proposer from the acceptor? Take 2 minutes and discuss.
Just propose a value.
All right. So, what did you come up with? Why do we separate them? Why does that make sense? Could you come up with a particular design situation where separating the proposers from the acceptors made sense?
I have a question about what a proposer is. The slides just say that it proposes values, but what does that mean by proposing a value?
Remember, what I said was we have a database with a single value in it. It says, I'd like to set the value to, and whatever it proposes, 42. So I'd like to set that value to 42. And I am keeping it deliberately opaque because what we're going to find as we keep moving through this, we use it for different things at different times. So the concept is, it's just something we need to decide. It could just as easily be, what are we going to have for dinner tonight?
Okay, makes sense.
Which is actually a really good example of what you might use a single Paxos for, right? Because you don't have 3 dinners tonight. You have 1 dinner tonight. Great. Thank you for the analogy.
So welcome.
That's great. But back to my question, which was, why might we separate the proposers from the acceptors? You don't have to. I don't know, Is he a proposer, an acceptor, or a learner?
Definitely not a learner.
Well, just because he is a learner doesn't mean he learned anything, right? All right. Well, good. That's something for you to think about. Oh, you thought I was going to give you an answer? No. This one you're going to have to dig for, because it's going to force you to think about the problems that we're trying to solve. So as we're going through this, think about that. Maybe the answer will become clearer to you. All right. So in phase one, what we actually have to do is figure out what's already been accepted. So the proposer sends this ballot message that says, "Hey, I'd like to propose this," and the acceptor then has a and this is Paxos. You could build other protocols. This is Paxos very specifically. I'd like to. So the acceptor gets it and it says, I will vote for it if the ballot number is larger than any ballot number I've already seen. And this is here because we're trying to break that race. There's no locks here at all. So we're trying to break that race. So if I accept a ballot because it's already higher than the highest promised, it's because I have already said, protocol-wise, I will not accept a lower ballot than the highest number I've already seen. But I can accept a higher numbered ballot. What does this do? Any mathematicians in here? Anybody ever studied set theory? There's this thing called the axiom of choice. What this is doing is it's forcing an ordering. And that's its function. It doesn't block you from accepting higher numbered proposals. It only says, I won't accept a lower numbered proposal. And if it's the same numbered proposal, then it's just a duplicate, and you don't do anything with it. So if it's a duplicate, in fact, you would send back the ballot and the value that was approved, that was accepted. Otherwise, you can just ignore it. You can reject it. There's no requirement that you reject it. The reason you might not want to reject it is because you don't want to flood the network with traffic. Yes?
Are we talking in this case when there's one proposer, or are we considering multiple proposers?
It actually assumes that there could potentially be multiple proposers.
So then, if it's doing the ballot thing where, like, say, the proposer 1 takes the ballot, proposer 2 takes the ballot, but then proposer 2 submits its ballot first, will proposer 1 have to take another ballot because they're...
If proposer wants to propose an additional proposal, it will have to build a new ballot. That's correct. Because proposer 1 can't, once he sees somebody higher number ballot, this is where it gets a little fuzzy. Okay, so if he, so what will happen normally, let's simplify this and ignore the edge condition for a moment. When proposer 1 sees the proposer 2's ballot and says, oh, this is higher number than mine, proposer 1 is basically going to say, then I'm going to assume mine wasn't adopted. But there's that window because of latency that says, maybe I did get an agreement. In which case, I just haven't received the messages for it yet. And that's why I said, let's start with simple and then say, but in reality, we still might have that proposal accepted. But I can make the same proposal, I can propose the same change on a higher ballot number. Yes, and that's what's going to be really interesting about this. And it's going to affect the way that we develop this protocol. That was an excellent question. That's a really good question. So the proposer is going to wait until they actually get a quorum. Or, and this is what really happens, a timeout occurs. In other words, I haven't received enough votes within a finite window of time.
What's the proposer talking to get these ballots?
The network.
But, okay, like, is there an entity it's talking to? Is it
Other nodes. Right, so in our model, all these things are nodes. And we can have a proposer, an acceptor, and a learner on the same node. so they'd have the same network address, basically. Or we can have a proposer, an acceptor, and a learner that are on different nodes. Or we can have any combination thereof. So we get what? 6 different combinations, possibly. Let's ignore the empty set, 5. So there's enough flexibility there right now. And that kind of goes back to that question I asked before, which is why might you have proposers and acceptors separated? Which we still haven't actually answered. And I don't want to answer that. I want you to figure out why you might want to do that.
Sorry, I'm still a little bit confused on the highest promise one. Is it something that the acceptor already knows, or is it something that the proposer says that?
If he's already seen that ballot and accepted it, then he's going to say that I've already accepted a ballot with this higher number. I'm going to either drop it, or, depending on your protocol, I could refuse it. But a drop and a refusal are considered to be the same thing in the Paxos protocol.
What if do I only ever process one ballot at a time?
No.
Yeah, if it's completely unrelated value, then I'm allowed to.
Right.
Yeah.
Only one value. Remember, I said I'm only going to decide one value. What are we having for dinner tonight?
Okay.
I mean, it would be kind of confusing to decide that you're going to have 2 different things for dinner, unless maybe you're hungry. Reality sneaks into these things. All right, so literally all this does, it says I won't end up with 2 separate decisions being adopted. But it's also very racy. Literally, if you have 2 different proposers and they each go trouncing on one another, you're never going to make a decision because they're not going to get a quorum because there's constantly going to be this churn. But that's not a protocol problem. That's an implementation problem. If you go and read the RAF paper, what they say is we're going to bound our messages by 150 milliseconds. Well, that's okay. That's fine. 150 milliseconds sounds perfectly reasonable as long as you're on the face of the planet. But when your single ping time to your satellite is 50 milliseconds, actually even not, it's probably not even very good on the face of the planet. When you have a data center in South Africa and a data center in, I don't know, Singapore, which isn't quite the opposite ends of the Earth, but it's sort of far away, and actually it's probably farther away because of the way that you have to go through cables to get there. The propagation delay there is going to be 100 milliseconds. So 150 millisecond timer doesn't work there anymore. And that's the only reason I reach for that. Okay, so where are we going to go with this? Why does this phase exist at all? Remember, what we're looking for is quorum. And the interesting point here is that if somebody else has already made a decision, what I'm going to end up seeing is at least one of the people who votes for my proposal is going to actually point to the previous decision. Now I just violated my whole thing about we're only making one decision. But, no. I only need one proposal still. Because anybody who wants to read what was that proposal needs to get a quorum. They need to read a quorum. And their read of the quorum is going to find the overlap by finding the one, at least one node, that has the highest number. So I have to read from enough nodes to form a quorum, and then I just simply take whatever the most recent ballot adopted was. I know there is a most recent. Maybe all of them are the most recent. Maybe everybody has exactly the same state, which is what typically happens when nothing's going wrong. But I don't know that until I've read the quorum. So the time it takes for me to read a value in this distributed consensus quorum-based system is the time it takes to read the last element of that quorum. I mean, if there's 101 nodes, and I use something slightly more sophisticated, like this is where using a matrix begins to make sense, because now I'm bounded by the square root of that, which is 11, because we're going to round up. So I only need 11 nodes. So the slowest of those 11 nodes is going to be all I need. And most people don't build 101 node Paxos clusters, I can tell you. But when I'm building a 5 node Paxos cluster, which is a common number actually, 3, 5, 7, they like odd numbers because odd numbers can't have, you can't, there's no benefit to having an even number. Because you still need, if I have 10, I need 6. If I have 11, I need 6. Okay, fine. So there just seems to be this preference for odd numbers in the implementation world. It's sort of strange sitting here talking about why we do things and thinking about how we actually do it at the same time and trying to reconcile them. Sometimes it takes a second. So there's this witness, the thing that I keep calling W in the pictures. This witness is the common element between these two quorum. And this is how I know I'm reading the actual decision. And as I said, most of the time in the real world, all of the things that come back have that value. But when you look at the protocol description, what it will say is it takes the maximum value, the maximum ballot number, to determine the actual elected value. Because the maximum ballot number is in fact the decision for that single value. Remember, I'm only trying to do this once for one single value. What's for dinner tonight? So when an acceptor promises that it will accept ballot B, it says, I'm not going to accept any proposal with a ballot number less than B. Yes?
Can we go back to the previous slide once?
I think so. Let's hope the power holds out.
So, just to confirm, the witness is the one that has the updated value of the ballot, right?
The witness has the value that was adopted on the ballot that was ultimately accepted, yes.
So, is it the witness's responsibility to inform the other members of the quorum about?
No. The witness has no responsibility to inform the other members of the quorum that this has happened.
So what happens if I try to make another update to the value and...
You can't. Remember, what did I start off this model by saying? We're only making one decision. We'll get to the multi-decision case, but we're only making one decision. And honestly, the way that we do that is the multi-decision case, we cheese it. We actually just make a series of discrete one-decision things. And we're going to do it in a linearized fashion that we're going to call a log. And that is going to be our trick. And that's what most of this ends up being. It ends up being a whole series of tricks. That's why I'm spending a lot of time here to make sure you understand why we can choose one value once. And then the rest of it, then we'll say, oh yeah, here, hand wave, pay no attention to the man behind the curtain. Ooh, wow, look. The Wizard of Oz. Great questions, though. People are really... Because I think this is probably the most important thing that we talk about, is understanding this. And if you can walk out of here being able to go to somebody else, like, pick your dog or your cat or your goldfish or something and explain it to them, that'll be it is a win. Nothing amazes people more than you can sit in an interview and explain Paxos to them in a way that they've never actually heard it before. I'm not guaranteeing that's going to happen, but when you start talking to people who claim to understand Paxos and then you have a discussion about it with them, you find out they don't really understand it. And it's not a really difficult concept. It's just counterintuitive. So the promise that we're making is that when an acceptor votes for a ballot, it says, I won't accept any other proposals that come in with something less than that ballot. Now that doesn't mean I haven't already voted for those earlier ballots, but it says I won't vote for it after this point. That's why I said this is kind of a race, right? You're proposing one value, oh, we're gonna have tacos and I propose pizza. And so you get a couple of people who vote for tacos and then I get a couple people who vote for pizza, but we don't have a quorum. And so you come back and say tacos, I say pizza, and we split the vote again, and we keep doing that. That's what can happen if you don't implement the actual implementation. So with implementation versus the protocol matters. The protocol doesn't care about racing. The protocol cares about making sure that you only make one decision. The way we're going to fix this in the implementation is we're going to put in an arbitrary delay. So when I notice that you have sent out a proposal, I'm going to wait for a little while. And then I'm going to send my proposal again under a higher ballot number, and that's going to allow us to add that randomness in there that we need in order to not sit there and constantly race against each other. It's essentially what happens in Ethernet, believe it or not. Anybody know how physical Ethernet actually worked? Okay, so the original Ethernet specification was for coax cable. Literally like cable like this thick. And it was yellow. I don't know why they picked yellow, but it was very, very banana yellow. And every 3 meters it had a mark on it where you could put what they called a vampire tap. It would literally pierce to the center through the sheathing, and it would create a connection that you could then use to send signals on the wire. Why every 3 meters? Because other people could be on the same shared wire, and this allowed us to detect when we were colliding with each other. So the reflection points. The 3 meter thing is the problem is that these things are waves flowing through the cable. And, okay, for the first 64 bits of transmitting on a piece of coax cable, there was the possibility, 64 bits, 64 bytes. Maybe 64 bytes. There's a certain number of bytes here. I'm not going to fabricate it. I'm just going to say there's a certain number of bytes that you send in which you could collide with someone else. And that's the actual thing that limits the length of a piece of Ethernet cable. Because there's a propagation time, 100 meters. That's the amount of time that it would take for you to interact, bump into anyone else who's trying to use this shared medium at exactly the same time. And you can detect that they are also trying to use it, and then they do a back off. And then they say, we're going to do a random back off. And because I back off for, I don't know, 5 milliseconds and you back off for 3 milliseconds, next time I'm going to see that you're already sending on it, and I'm not going to send on it as well. So these kinds of race conditions happen in the real world, and the way that I'm talking about breaking it is exactly the way that we've been doing it for a long time. Now, when we talk about modern Ethernet, what it is, it's mostly cables you plug into the wall and creates a star topology. You don't have that kind of shared media. Wi-Fi is shared media, though. So again, we still do this. We still have those kinds of exponential backoffs. I mean, you probably don't have any problems like that because, of course, UVC Wi-Fi is spectacular. Has anybody had any problems with UVC Wi-Fi? Is there anybody who hasn't? So this is how we are detecting our collision on our shared media. I see a higher ballot number. That means somebody else is trying to use this as well. And what we're going to do is we're going to actually break that in the implementation by using that random backoff. But the protocol doesn't specify what the random backoff is. The implementation standard does. So the reason this works is that acceptors have agreed to reject any lower numbered ballot. Eventually, somebody gets that higher numbered ballot in there, gets enough votes back and says, aha, I have a quorum. So here we go, another 2-minute exercise. This time, what? Oh, I'm looking at the next slide. My phase 1 exists, and I've done that. Right, now we're back to here. This is the promise. I went the wrong direction. And the problem is, it shows me the slide that's next on here, and I have to look up here. Okay, right, so 2 minutes. What does the proposer do with the responses from phase one? What happens if he gets different previously accepted values? Which one actually matters? I did remove that from the...
Maybe it's like the promise part that we talked about. It's like none of the values really matter other than the highest one.
Oh, it doesn't send the value. Right. That's right. Forget about that.
What I'm thinking is like, what if each person just says something?
All right. What'd you come up with?
Oh, but right now the only one who's supposed to answer is
And I was looking through the next slide and going, aha, right, I'd forgotten about that. Right. The ballot doesn't actually need to include the value. The ballot is just choosing who has the right to declare what the value is. There's no harm in including that value, but by omitting it, you can reason about this without worrying about what the value is. Anybody come up with a reason why? What does it do with the responses from phase one? Well, the next slide kind of answers that. Did you? Okay. You know, I'm angling for anybody to say something besides me, because I talk too much. So, he gets back these accepts from people, and what he looks at is he says, if anybody says they've already accepted a previous value, then that's the value with the highest ballot number. Ah, right, because the accepts come back with the highest value I've seen. Or the value of the highest ballot I've seen. That's correct. Right. So the proposer either uses the value of the highest ballot it hears about, or it uses its own value. So now that's why as I was looking at the slide, the proposer has a value, but hasn't proposed its value. It's just proposed that it gets to choose the value. That's the distinction here. That was wrong, actually. It does send values. So the ballot and the value. The proposer can use its own value if nobody else has seen a value. Otherwise, it will use the value of the highest ballot that answered. So he's got enough for a quorum. He's going to choose a prior value that was already suggested, not the value that he wanted to use. So he only uses his value. Do you see why this happens? This gets him out of the problem of knowing what value the other people have already accepted. Because all those acceptors, the highest number guy has accepted something, and now all he needs to do is say, I have a quorum here, everybody here is at or below this ballot number, so we're going to take the most recent ballot. And I now have a quorum, so I get to choose that value. And I'm going to choose the highest value that's already been voted for. I'm only going to substitute my value if nobody has a pre-existing value. So if I sent out ballots to people and said, "What's for dinner?" and you said, "I'm going to vote for your dinner suggestion." You suggested pizza, and your response back says, "I'm going to vote for you," and the last thing I saw was nothing because I hadn't seen any proposals yet. Then I get to count your vote as a vote for pizza. If, on the other hand, your message gets to me and it says, "Well, I voted for tacos," and I look and I say, "His ballot number is lower than yours, so, well, it's tacos it is." Or, "His ballot number is higher than yours," in which case his ballot number didn't have a value in it. Ahaha, it's pizza. The choice doesn't actually matter here. That's the interesting part. We're not arguing about who's more right, pizza versus tacos. We're just simply trying to agree on a protocol that guarantees that we'll only choose one. And remember, we're only choosing that one value. So the value is decided when it's been accepted by a quorum. Now that doesn't prevent us from getting into those race conditions I talked about. Those race conditions can still happen. We're going to break that by putting some timers out in here, some timeout values.
Like, does the acceptors check with every other acceptor?
No, they don't check with each other. They only check with, the only one who knows what the acceptors are saying is the proposer.
How does the, like, let's say I'm a proposer. I propose some value, and I had a high ballot number, and without ever waiting, like the acceptor to respond, I say accept.
You can't do that. That would violate the protocol.
Okay.
Right. So the protocol is that the proposer can't send an accept until it has a quorum.
Okay.
That's the reason that you don't have. If a proposer did that, it would be violating the protocol.
Okay.
And that's going to be my ticket out. Is that if you misimplement the protocol, yeah, you're going to be in hell debugging it at 3 a.m. So there was a hand back here briefly, and then I saw two hands pop up here, and I'm not sure which order.
So if I understand correctly, phase 2 is essentially a way to update the other nodes.
Phase 2, the accept phase, yes,
Okay.
is in fact exactly that.
Okay.
So if I don't get a quorum, I can't ever send an accept. And it's like everybody just keeps voting. And that's why we end up with that race condition that I was talking about. I don't know, I'll do the one on the right and the one on the left.
So one, in this case, it says the no acceptor sent back the value. The proposer just uses its own value.
Correct.
But doesn't that mean that if no acceptor sent back the value, it was just rejected? So then, it's like it said you use like
The acceptor has not accepted any other ballot thus far. That's all that really says.
How do you know that that's the case, or it's just been ignored?
I'm not sure what that would mean in this.
Like in phase 1, it says otherwise reject or ignore.
Okay, but that's because that acceptor has already voted for something.
So then how, as a proposer, you know that they haven't sent anything back because they haven't received anything prior, or because...
Well, it was sent to a different proposer. Right, the acceptor, this isn't a broadcast protocol, it's a unicast protocol. So the acceptor could have sent the answer back to a different proposer. So proposer A and proposer B don't get to see the accepts that are sent to the other party. So that's why that would happen.
Okay.
Does that make sense?
Not particularly, but it's fine. We can keep going.
No,
Well, I just don't understand the difference between, like, if nothing comes back, the difference, like,
If nothing comes back, in other words, if the acceptor comes back and says, I haven't accepted anything previously.
sure, how do you know that versus it was just rejected? Because the ballot was less than the highest promised.
Then the acceptor would have sent back the ballot, the highest number proposal it had accepted. The acceptor sends back the highest thing
Oh, well,
it
that's
has
not what
accepted.
phase one says. Phase one just says rejected or ignore.
No, phase one says what you do when you receive it. If it, okay.
Sorry, no, it's.
I think you're missing the fact that phase
Yeah.
one, or the slide is wrong, which is certainly possible. In phase one, it says, so we send that out. An acceptor responds if the ballot is greater than the highest promised. And that is the acceptor saying, I won't accept a ballot with a lower number. It doesn't respond if it has, let's see, right. It doesn't respond if it's not greater than. So this is the else clause. So I'm looking at the slide here and you're not, so of course it doesn't make any sense. Come on. There. I was looking at the next slide. Okay, so you're looking at the else clause and saying, I don't understand that. But I think you're missing the fact that if the ballot is greater than the highest promised, then what I'm going to do is I am going to respond with an agreement that you're the highest numbered ballot and I will not accept anything with a lower number on it. Does that help?
Yes, I think so.
Okay, all right.
We'll keep going.
I'll go with that. And if it doesn't, then we definitely need to work through that. And I'm probably not helping because I say it's simple, and yet every time I walk through this, it's like, it is simple, but it's not.
I had a question about this symbolism. This if block clarifies that.
Okay, good. Yes.
Wait, so if I'm understanding this correctly, right? You have the witness in this quorum, and this witness is the person, like it's like the brain of the quorum, right?
No, the witness is just one of the acceptors who actually saw the highest numbered ballot. We know there's at least one witness. Now, in that picture, we keep putting one witness because that's the minimum number of witnesses. But in the real world, most of the time, all of the acceptors have accepted the ballot. Everybody sees it. So the problem is whether it's one witness or n witnesses, you still have to get a quorum worth of them to know that you're seeing the highest numbered ballot that was adopted.
But the surrounding nodes can have higher ballots than the witness, right?
Right, but those do not form a quorum.
But then they are talking to the witness to update everyone's values.
No, this is a read, not a write. So, okay. Scenario. We're only making one decision. Once we've made that decision, we're done. What are we having for dinner tonight?
Yeah.
Pizza, tacos, I don't know, if somebody wants something different, sushi. There. Well, let's say we have 5 people and each of them proposes something different.
Yes.
Because that would never happen when we're talking about what to have for dinner tonight, right? Of course not. And everybody proposes it at the same time.
Yeah.
Nobody gets a quorum. Everybody proposes again. Now they update their ballot numbers because everybody was above them, except for the last person to propose, and then they're going to update their ballot because they're going to collide as well. And we're going to keep doing that. So what I said was that in the real world, in the protocol, in the Paxos protocol, that can happen.
Yes.
And that the problem with that is that it doesn't provide liveness. It provides strong correctness, but not good liveness. So we give liveness to a system in implementation by using random backoff. So you don't send another ballot for a certain amount of time. And then eventually what will happen is we'll come to a decision. When we come to that decision in a group of 5, 3 of them will have seen that. And there's no other quorum that won't have seen the decision that we're going for sushi.
And then all 5 goes for sushi.
And then all 5 can go for sushi, right? But there's the adoption side, which is the right side. And then there's the what happened side, which is the read side. So if you want to read something out of the system, you have to read a quorum of nodes. Even if all 5 have exactly the same values, you have to read a quorum of nodes. And the reason I mention that is because when you're really implementing it, that's one of the costs associated with Paxos. I have to read multiple nodes. And that should have hinted at what question 1 was. Or was that question 2, the one about the acceptors? Why do you separate proposers from acceptors?
So for
Oh, he doesn't want to answer the question. He wants to ask another one. Okay, great.
sorry, so for the case 1, when it says like promise not to accept no ballots, does that mean that when it see like the ballot from the prepared request, we'll just save it, and then if anything else comes, we'll accept it?
Well, it won't accept anything lower numbered, but it can accept things that are higher numbered.
Okay.
Right. So the ballot numbers have been constructed so that they are always increasing. So if you start a new proposal, your ballot number is higher than anything you've already seen. And I won't vote for any ballot with a ballot number less than anything I've already voted for. So I guess that's kind of an at most once and at least once kind of binding that we're doing. Hadn't really thought of it that way. Okay, so now the proposer says, I have a quorum. And okay, why are we going to do this? We're going to do this because maybe we've got some packet delays and things are out of order. So what I'm going to do is I'm going to send that accept. The acceptor is now going to say, okay, you're right, I accept this. And now the acceptor knows what the decision was. It's now become a witness. Otherwise, it actually has to actively reject it. It has to say, no, sorry. And in that rejection, it's going to say, here's the higher numbered proposal. Here's the higher numbered ballot. The highest numbered proposal by ballot number that I've accepted to replace what you just said. So this is the other side of the race condition. Maybe while we were in the middle of this dance, somebody else got in there and said, burgers. You're like, burgers? Again, all we need to do is make sure that we've got our witness somewhere in every quorum.
I have to double check because Gemini could just be wrong.
Gemini's probably wrong.
Does
But
everyone in this quorum act as the proposer? Does each of them act as proposer and then maybe the other knows
No.
the acceptors? Okay.
no. In fact, if Gemini told you that everyone has to be a proposer, it is wrong. Because that is, in fact, not correct, and there are reasons. In fact, one of the open questions I gave the class was, why aren't the proposer and the acceptor the same thing?
Why aren't?
And right, why aren't they? In Paxos, proposers, acceptors, learners.
Is it because if the proposer and acceptor are the same node, the value that I am proposing, I am just accepting my own value?
Well, you are doing that, but in fact, the reason I think is more pragmatic.
Because the ballot that I choose at that point in time, it will be the highest that I have seen. So I will always be accepting that.
And you're looking at this as a protocol consideration, and I'm actually thinking that it's as much an implementation consideration as a protocol consideration. What did I say we have to do in order to do a read in this system?
Something to prepare to, like something to prepare to itself.
No, if I want to read a value, I want to find that witness. What do I have to do?
Send a proposal to the acceptors and then
You don't have to send a proposal to them. You just said, well, I guess you could do it through that way. I hadn't thought about that. But you have to query all of the acceptors. So the reason you might want to allow more or less proposers is because the expensive part is in fact querying the acceptors to find the quorum. So you might want to have fewer acceptors than you have proposers. Or you might want to have more proposers than you have well, that's the same thing. You might want to have fewer proposers than you have acceptors. By separating them, you have flexibility in designing this to meet specific needs. If we put them together, there's actually no structural benefit to that. And as you pointed out, you're basically just ending up voting for your own thing. It's going to restrict your flexibility. And we're trying to build a general model. Lamport is building a general model here, not trying to solve a specific problem. When you look at Raft, they're trying to solve a specific problem. That's why they nailed in 150 milliseconds. And what is Gemini lying to you about now?
I haven't read it all.
Okay. Yeah, Gemini, they're all very verbose. I have something in common, obviously. Let's do this. Okay, so why do the highest ballot wins? Ballot 5 chooses some value v, which has been accepted by a quorum. Now a new proposer runs phase 1 with ballot 7. And here's the interesting problem. The new proposer's phase 1 quorum intersects the phase 2's quorum that chose v. Remember I said you take the highest value that comes back from the accepts? So the new guy only proposes higher ballot number, but he only proposes the value that's already been adopted. So once it's been adopted, you can still have another person come along and propose it, but they can't change the value. That is what's giving us our immutability. That's what makes the decision persistent. Even if the world gets a little out of whack and the state doesn't propagate properly, so we end up with some sort of some proposer who's trying to say, no, I really want, I'm running out of food, kebabs. I really want kebabs. I send my messages out, I say, hey, I want to do kebabs, and people come back and they say, well, the highest thing I saw was burgers, because burger snuck in there at the end. The highest thing I saw is burgers, and he looks and says, well, I have to propose burgers now. So all he can do is propose burgers. So any subsequent proposal, this is what's cool about it, will in fact always have the value of our witness, the one value that is common to every quorum. At least one value that's common to every quorum.
So in this scenario, we are assuming that the acceptor can only accept one thing. And then
We only are deciding one thing, what's for dinner. We will get to it, believe me. Might not get to it today, because this is good, because I think this is really helping me explain it better.
Acceptors can respond back with any value, any previously seen value, correct?
Highest number. They have to stick with the highest one that they voted for. The value from the highest number ballot. But an acceptor might respond with one value at one point in time, but then accept a higher numbered ballot and then respond with that higher numbered ballots the value, and next time. So in other words, we can all be sitting there talking about pizza, sushi, kebabs, burgers, whatever else it was, tacos, but and an acceptor might be sitting there going, handing those back at different times with different ballot numbers, but eventually this will converge to a point where there is in fact a quorum that's accepted a ballot with a value. And once that happens, in other words, once we know there's a quorum, we know that even if someone else comes in the door and says, hey, I'm late, I don't care, I propose, oh my gosh, chicken, fried chicken, and beer. Well, and then of course it all wins because of the beer. But it's too late, sorry, you already decided. You already decided on burgers. Kenny keeps track of what he decided on, right? So the point is, he's going to propose beer and chicken. Notice it now is reverse to the beer first. So he comes in late, he proposes chicken and beer, and he sends that out, and he gets people back saying, well, actually, the last thing I voted for was burgers. maybe somebody comes in with Paxos, but one of those is going to have a higher ballot number, so he's going to take the higher ballot number and he's going to say, that's the only one that could have won, therefore that's the only one I can now propose moving forward. And even though he wanted to offer chicken and beer, we're having burgers, because that's the only one he can propose moving forward. So even a ballot that comes in late will still have the value that was adopted by the quorum. He's got that hand like really below the screen there. Go for it.
Okay.
I was just going to check and see how close to dead I am.
So my understanding, like, I think this ties to the previous question as well. So my understanding is that here, both phase 1 and phase 2, we only sense out like the most updated value, right?
Phase 1.
Phase 1 and phase 2. So
Okay, so phase 2. So phase 1, the proposer is allowed to propose anything. In phase 2, the only thing he can propose is his own value if no one else tells him that they have voted for a different value. Otherwise, he's going to just simply propose the highest, the value of the highest adopted ballot. I mean, in essence, what this is it's a race condition that tries to converge to something. So if we're all proposing different things, what ends up happening is, by doing that, like I said, in the implementation, we'll end up doing that exponential backoff kind of thing. By doing that random backoff, what's going to happen is we're going to start seeing the same value appear in all those higher ballot numbers, and that's why we converge. The reason to do that is we eventually do want to converge on a decision. If we don't put things in like the time boundedness, the variation there, then you really can end up with liveness problems. But a little bit of randomness actually solves that issue. And I'm hedging back and forth here because Paxos doesn't require that you do that. Paxos just says, if everybody wants to keep shouting and choosing, proposing different things, that's great. But the moment one of you runs out of breath to keep shouting, you're probably out of the race. So maybe it's just the most long-winded of us that wins. And I'm 11 slides into 19. I was like, this will be a nice short day. No! Good. Excellent. All right, so the highest ballot wins. We always have at least one acceptor that reports the highest ballot, and therefore any new proposal can only send an accept with the previously adopted value. And that's the clever part here. You can keep sending proposals, just keep sending them higher ballot numbers, and that's going to be really important when we generalize this and we move into multi-Paxos. Because what we're going to do in Paxos is just decide that one value, what's for dinner, and then we're going to change that question to who's our leader? Because that's going to be the trick that's going to allow us to adopt a leader. In Raft and view stamped replication, the decision is based on the network address. In Lamport's system, it's not. The ballot numbers are typically chosen by some sort of process ID, which in a network ends up being some network number or something derived from that network number, but it's not a fundamental property of the protocol itself. He doesn't define how you choose those ballot numbers. He just provides a clear demonstration of how he did it in a concurrent system. So the key invariant here is that if we have a value that's been chosen, any higher ballot proposal can only propose V because it can't actually send out an accept on its proposal without having intersected with the quorum. So it has seen at least one of the witnesses to the quorum. And since it cannot propose anything other than the already adopted value, we can sit there and we can keep sending out ballots, and it really does happen in real production systems. You will continue to use higher numbered ballots to propose the same value for the same decision. And eventually we give up on that because nobody wants to propose a new value for something that's already been decided. So this gives us this observation that says if we have two different values that have been chosen, then that implies that they are the same value. You can actually express this in TLA+. That would be an invariant in TLA+ that says this has to be true. And if it finds some path through the design space that says it's not true, you have a violation. You have an invariant violation. And it'll not only point it out, but it will actually show you the flow of control through the system that got to that invariant violation. The reason to use something like TLA+ is to debug this in a model rather than trying to debug it when it's in deployment. Because debugging things like this in deployment is really hard. And I can drag this out for a few seconds more, but I'm not going to do this, the checkpoint. I think these are useful. I'm going to make a decision here. I'm actually going to wait and do this on Thursday. So I might have to push things out a little bit further, but I think this is super important. And if I give you from now until Thursday, you can spend lots of time not thinking about it. So that when you come back on Thursday, you can take that 3 minutes and then walk through that and make sure that people are comfortable with that and understand it. Because if you don't understand this, everything else that follows is going to just be like, why am I doing this? What is this doing? How does this work? So this is like the fundamentals. No, it is the fundamental. In Paxos, in terms of the way that we actually build these general purpose distributed databases, this is really important. So I'm going to end it here, and I will shuffle the slides around and continue this conversation on Thursday. So this Thursday slides are there. They will change because I'm going to move some stuff around. So thank you, everyone, and I'll see you Thursday.
On my last slide, you mentioned BP1 implementation. You today elaborate what was supposed to happen?
The display, the design project, is it in the slide? I put information in too many places, right? So we moved design project. Did we move design project 1? No.
It says on the slide, at the very last slide, it's like BP1 implementation. It's not clear.
No, because I moved it out, right? So as long as I moved it out, it was in the original slide template. And since the same information is in like multiple spots with no coordination protocol, I screwed up. I just, honestly, when I was looking through the slides, I kind of just don't even see that slide. You're right. Okay. Yeah, my bad. You are right. It is wrong. I will have to fix it. And let me stop the recording. I did this without running out of battery. That is kind of shocking.